All right, so this chapter we're going to be looking very briefly at intermolecular forces. We'll skip most of it, but I want to give you a basic introduction to the different types of intermolecular forces that come into play. The weakest are London dispersion forces, sometimes called weak forces. Van der Waals forces I've also heard used for the similar effects. And these are forces between, well, it says nonpolar polar molecules, but really between any molecules or atoms. We induce temporary dipoles can be induced. And the temporary dipoles mean you have a distortion of the electric fields, basically between a distortion of the positions of electrons around an atom to cause a very temporary dipole. Again, around an atom, electrons are not in fixed positions. They move about freely within their orbitals anyway. And so they may be on one side of the atom or the other. And you can actually get a polarization of these electrons to create a temporary dipole. And polarizability just indicates how easily a given atom or molecule can be polarized. So let's look at, just to show you briefly, or kind of qualitatively, what's happening here. If we take two atoms, however many, whatever the nuclear charge is, and they have their electrons spread out about them, fairly uniformly. As these guys come near each other, the electrons first encounter the other electrons, or their electric fields are interfering with each other first, and so you can actually get temporary shifts in the dipoles. You might get this atom might have its electrons shifted more over to the right side, only a couple over here. So you get a temporary dipole induced in this atom, so it has a slight positive charge on the left side, slight negative charge on the right. This other atom, now that you have this slight dipole, you might have a slight dipole over here. The electrons might, in the atom on the left, might be more attracted to this nucleus over on the right, because now they can see you have less shielding effects going on. So you get a temporary dipole induced here. Again, the electrons are just moving into other parts of their orbitals to create a very temporary dipole. And this causes a very weak, very temporary attraction between these atoms. And the same thing happens for molecules also. And so this text says, the text says this is between nonpolar molecules. Well, it really occurs between any molecules and atoms, not just nonpolar ones. But the thing is, with polar molecules, you won't notice this effect because the polarities of the molecules are, have a much stronger effect. So this temporary dipole, or the temporarily induced dipole, would be overwhelmed by the actual polarity of the bonds themselves. So you would not notice that. That's just what this is showing, inducing temporary dipoles as molecules or atoms come near each other. How close to come, the types of atoms involved, the bonds involved, all these will affect the polarizability of these atoms, the molecules. So a few things that affect the strength, the size of the atoms and molecules. Larger shapes, larger atoms, larger molecules are more easily polarized. Again, it's still a temporary effect. Just because the outer electrons get shielded from the inner from the nucleus, and you have a much larger distribution of electrons anyway. And so they're just much more easily polarized. Shapes also makes a big difference, depending on often called steric effects. If you have a linear molecule where two adjacent molecules line up side by side, you have kind of a cumulative effect. Polymers are, in many cases, nonpolar hydrocarbons, very, very long molecules, hundreds of thousands of atoms long in some cases. If they can line up side by side, every atom in that chain can be attracted to atoms in the nearby molecular chain, and it can add up so that it can make these molecules want to stay near each other. Because you don't just have one atom attracted to one atom on a molecule, you have bunches of atoms in one molecule lined up next to the atoms on the other. So, so the sizes and shapes can make a difference. Again, I just wanted to vaguely or briefly mention this right now. We'll go into some more detail on 1 to 5 and 6. And the rest of this we're going to gloss over. I really want to get to discussing a little bit about interactions between polar molecules. This is very critical and a little easier to visualize, and really more, I won't say important, but more generally, it explains lots of natural phenomena you're already familiar with. So, dipole-dipole interaction. This is attraction between dipoles in polar molecules. As we said, dipoles, when you have polar bonds, they form a polar molecule. You have a slight positive, slight negative into these molecules, and it ends up acting sort of like a weak ionic bond. So if we have HCl molecules, so they're in gas phase, they come near each other. Well, chlorine is more electronegative. It has a slight negative charge on the chlorine atom, a slight positive charge on the hydrogen atom. So when this comes near another HCl molecule, you're going to have this weak attraction between this slight negative charge and slight positive charge. Again, it's still much weaker than the covalent bond holding the molecule together, but it can be fairly significant. And you can have, this hydrogen might be attracted to more than one nearby chlorine, and same thing over here. So what this means is that these HCl molecules really want to stay near other HCl molecules. Compare this to, well, let's look at one more first. Let's look at water. It's a really good example. Our water molecule, but remember this is not linear. We have our slight negative charge, our slight positive charge, our slight positive charge. Excuse me. So let's draw this more like a bent structure. When water molecules approach each other, well, the positive and negative ends will orient towards each other. You just flip around so you get this attraction between nearby water molecules. So you get attraction between any partial charges and any other nearby partial charges of the opposite sign. So water molecules are attracted to other water molecules. In fact, this is why water is a fairly unique molecule, because it's actually very small, very polar, and there's a very strong intermolecular force, intermolecular attraction between the adjacent water molecules. That's actually the next section discussing hydrogen bonding. But really wanted to show you why this is fairly significant compared to, let's look at nitrogen molecules. Nitrogen, looks like that. Very nonpolar. So if you have the nitrogen we're breathing, for example, all these nitrogen molecules around, they have almost no attraction for each other. They do have some, the van der Waals forces or the London dispersion forces, the weak forces we just mentioned, but that's insignificant under most conditions, unless you get to very, very low temperatures where the molecules move very, very slowly. For this gas, that won't be significant. And this also shows how significant the intermolecular forces can be. In most cases, with everything else being the same, a heavier molecule will boil at a higher temperature than a smaller molecule. Nitrogen is actually a slightly heavier molecule than water, but water boils at a much higher temperature. Nitrogen boils at like minus 250 degrees centigrade or so, maybe 220, I forgot the exact numbers now. Water boils at 100 degrees centigrade, so it's over 300 degrees higher temperature, and that's all due to the attraction between one water molecule, if I can talk. That's all due to the attraction between one water molecule and nearby water molecules. Again, these intermolecular forces are weak. They're still much weaker than the covalent bonds, but it means that it takes a lot of energy to separate one water molecule from the other ones. So that's why water has a very high boiling point. So that's really when what's mentioned here. Hydrogen bonding is a type of dipole-dipole interaction. Water, in particular, is really a good example of hydrogen bonding. It's really one of the strongest dipole-dipole interactions you can have. It occurs between a hydrogen atom bound to a small electronegative element, which basically means fluorine, oxygen, and nitrogen, and an atom of oxygen or nitrogen in another molecule. And really, to show you more detail what that means, let's go back to water. Well, it's not just dipole-dipole interaction. Or at least why it's more significant. You really have attraction between this hydrogen, since the oxygen is so electronegative, it withdraws electrons from the hydrogen, so it makes this very polar bond. So hydrogen has a very strong polarity to it. And you have these unshared electrons over here versus just a dipole, that makes a very strong attraction between adjacent molecules. Because of the very polar nature of the bond, you get, again, a slight positive charge on the hydrogen, and these unshared electrons on a very electronegative atom just results in a very strong attraction between these molecules. And that's what we mean by hydrogen attached to a very electronegative atom on one molecule and release the unshared electron on the electronegative atom nearby. So that's going to be oxygen or nitrogen. So that's really hydrogen bonding. But again, be very careful of the term bonding. I wish I could delete that term and call it hydrogen something else, but it's been around for so long. So with hydrogen, people tend to think hydrogen bonding means the hydrogen-oxygen bond, but that's not what it means. The hydrogen bond, or H bonding, is used to refer to this one type of intermolecular force. So just be careful about that term. It's easy to get tripped up, but just have to get used to it. That's the term we have. And this shows the same thing. It's not just between one molecule and the same molecule. Acetone and water, methanol and water, ethanol and water, all have very polar bonds. You get dipole or hydrogen bonding between all of those in all those cases. This is also very significant. This is what I mentioned earlier. The boiling point depends on intermolecular forces and the mass. All these molecules are fairly light. Excuse me, are light molecules, but water has the strongest intermolecular force, strongest attraction between molecules, so it has a higher boiling point of all these in all these cases. Methane, very nonpolar molecule, no interaction, so it boils at a much lower temperature than the other molecules. So again, you can use these for comparisons to determine which you think would be the lowest and highest boiling points. You want to pause and think about that for a second. All right, so in this case, the lowest, this is a very nonpolar molecule, so we expect that to boil more easily. There's no or very little attraction between adjacent molecules outside of the weak forces. Here, there actually are polar bonds. There's the CO and the CO bond. It's not exactly symmetric, so there's a polarity to this molecule. It's not nearly as much as with the methanol over here, but still significant. So this should be increased. This should be the lowest. It should have the second lowest boiling point, and this should have the highest boiling point, because with methanol, you can have hydrogen bonding between nearby methanol molecules, so you have a much higher boiling point. I think it would help to rank bond strengths. I'll put bonds in quotes. I'll discuss strongest to weakest. But I'll include intermolecular forces here. Strongest bonds are covalent in general. Sorry, kind of sloppy there. Ionic are next. I'm going to skip a bunch down here before I go to hydrogen bonding, because just want to stress that hydrogen bonding, these intermolecular forces, are much weaker than the forces holding compounds together. Then you have dipole. Then you have what are called weak forces. I've heard the same terms used interchangeably. London dispersion forces, or sometimes van der Waals. Or just weak forces. Those all mean the same thing, basically. So again, in rank, covalent bonds are strongest, ionic are next, and way down then you get to hydrogen bonding. Again, it's very significant for the physical properties of water, but it's still much weaker than the covalent bonds holding the water molecule itself together. And keep in mind, to keep that straight, when we boil water, we're not breaking the molecular bonds. We're just turning a liquid water into gaseous. We're just separating out the molecules, one molecule from the others. But the molecules themselves are not broken apart when you boil, when you go through phase changes. And then dipole are next. What happened to the rest of my dipole? I've accidentally erased it, sorry. And there are other types of bonds. You can have like ion dipole interactions, things like that get more complicated, but I think this helps just to visualize the ranking and strengths of these various bonds.